Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. Today's discussion is again on testing for stationarity. In our previous class, we have seen the method, basically the traditional methods of finding whether our process is stationary or not. Before that, we have seen examples of a stationary process in terms of autoregressive model and examples of non-stationary process in terms of random walk model. Then we have seen the method by Bartlett and all to check for an individual lag, individual significance of an individual autocorrelation coefficient. Now, nowadays, agreed, software is commonly used to find these autocorrelation functions and stationarity and all those things. But let us have a feel of how you compute this autocorrelation function. Like, see, we have taken a very simple data of only 5 observations, 3, 3, 6, 9, 9. So these are the number of observations, and then we are doing the calculation of first order autocorrelation function. So we have our actual data. For the first order, what we do, we just take a period lag. So this 3, it comes over here, this 3, it comes over here, this 6 comes over here, this 9, it comes over here. So we just take a 1 period lag. Okay, so this 6 is an extra number over here, just ignore it at the moment. So we take a 1 period lag, and then we take the mean of y. The mean of y means we have the numbers from here 3, 3, 6, 9, 9. We add all these and divide by 1, 2, 3, 4, 5. So we get the mean as 6. So 3 minus 6 is minus 3, 3 minus 6 is minus 3, 6 minus 6 is 0, 9 minus 6 is 3, and 9 minus 6 is 3. Then we take the square of it, that is 3 multiplied by 3, 9, 3 multiplied by 3, 9, 0 is 0, 3, 9 and 9. Next, we use the column in which a lag has been taken, that is yt minus 1. Now, we take 3 minus the value of y bar, which is equal to 6. The value of y bar is equal to 6. So we have over here, again, 3 minus 6 is 3. 3 minus 6 is minus 3. 6 minus 6 is 0. And 9 minus 6 is again 3. Then we multiply this column with this column. That is yt minus y bar multiplied by yt minus 1 minus y bar. So there is no calculation over here. We start from here. 3 and minus 3, it becomes 9, 0 and minus 3 is 0, 3 and minus 0 is 0, 3 and 3 is 9. Now the formula of autocorrelation function, rho k, and I have denoted it by 1, that is, we have taken first lag. So that is equal to summation of yt minus y bar multiplied by yt minus 1 minus y bar. So that is equal to 18 divided by summation yt minus y bar square. So yt minus y bar square, the summation is 36. So 18 divided by 36, that is equal to 0.5. So this is how we calculate the autocorrelation coefficient. Another example we have seen, that is now second order, sorry, please note this correction. This is basically second order autocorrelation function. Again, this is the mean, y bar is equal to 6. Again, the same process. Only thing is, now we take a 2 period lag, means this 2 is written after a lag of 2. This 3 is written after a lag of 3. This 6 is written after a lag of 2. This 9, I cannot write anything over here. I don't have a corresponding term over here. So I cannot write it over here. This 9, this is this 9. I cannot write it over here. And also the remainder of the 9 I cannot take. So our yt minus 2 restricts itself to only this much. Then we do yt minus y bar. This is the same thing which we have done, and yt minus y bar is square. In the earlier case also it was 36. Now next we do yt minus 2 minus y bar. Now my yt minus 2 is here and y bar is equal to 6. So 3 minus 6 minus 3, 3 minus 6 minus 3, 6 minus 6 is 0. Next, we do the multiplication of this column terms with this column terms. So, minus 3 this is not 0, rather it is x. So, it means there is no calculation. So, we get an x over here. 3 multiplied by x, we get an x over here. 0 multiplied by 3, we get 0. 3 multiplied by minus 3, we get minus 9. And 3 multiplied by 0, we get 0. The formula of RK2 is just like the earlier case, only change over here is in the first case it was yt minus 1 when we were taking the first lag, here it is yt minus 2. So when here it is yt minus 2, we need the summation of this, so we take the summation of this 9 divided by the numerator, that is the summation of yt minus y bar square, that is equal to 36. So minus 9 divided by 36 is equal to minus 0.25. So we had done the calculation of autocorrelation function at the first order and the second order, and subsequently you can go on calculating. It depends upon how much, what is the length of your series. The same thing has been picturized over here in terms of through a software. The software used over here is eViews. One thing I would like to tell you about eViews, it's a very user-friendly software, and one of the good things, although it's not a free software, it's a paid one, but the good thing is that for a short term, if you need this software, if you want to learn this software, what you can do, you can just go to the site, you can go to the Google and search it for eViews student version. There is a small performer to be filled and it needs only an email. There is nothing else is required, and you just send him fill that performer, and on the email which you are giving, you will get a link to the student version. Now this is student version of eViews. Although it doesn't contain all the options which are present in the full view, the full eViews, in the complete version of the software, but it will be more than sufficient for all of you. You need, and an email will come from this eViews company, and then they will give you an installation key, a software, and also along with they will give you a key. So you can download it in your system and you can work. The only bad thing is, although the number of options are fewer, but that is not basically a problem. The main issue is it is active for only 1 year. Only 1 year it will work. After that, the license would expire. So this is the process to. So we will be using. We will be demonstrating the output sheet of eViews also. Now, what we do, we are basically we are trying to draw this correlogram. This correlogram we have discussed earlier also, and we get a picture like this. So it is showing that we want to draw the correlogram of the series at the level in the first difference, and likewise. So we simply get this picture. Now, like I am showing you this picture where your autocorrelation function, they are declining slowly. So this gives a hint, and also the Q stat which we have discussed in our previous class, that is also given over here. So what we see that we can get a feel about what is this this data is stationary or not. Although it needs two things are there. It needs an expertise. in order to say whether there are rules, but many a times it can be confusing. So it needs an expertise, plus still it's not an exact, exact measure. You need to have, we will be looking at it. So but now moment, see, when we had taken the first at level, when we did not take the first differentiation of the data, we took the data as it is. Now the autocorrelation functions are quite high and they are declining very slowly. So this gives an impression that the series is not stationary. From the autocorrelation function, we can identify when the series is declining very slowly. We can say that these are called as spikes. The spikes are declining very slowly. We can say that this series is not stationary. Now next time what we do, we try to make the process stationary. We try to convert the data stationary into stationary. As we have seen how conversion is done. We have, say, 5, 6, 10, 50 and say 60. This is my data. I take it to one period lag, 5, 6, 10, 50, and then if suppose this is xt, this is xt, this is xt minus 1, x over here it is 1, 6, 10 minus 6 is 4, 5, 10, 50, 40 and 10. So this series, if it is not stationary, then we can make it stationary by doing the first order differentiation. Now when we do this process and then we put the same data x again in the software, and in the software we can give the option like we need not do the conversion like this. Like in the first slide I have shown you, we can do it at level or at first difference, or even some series they do not become stationary at first difference, they become stationary at the second difference. So that option is also given over here. So next time when we select, and this the second item will become highlighted, that is first stationary, then we see that the autocorrelation function is no longer like the spikes are not big and they are not getting reduced slowly. So from a visual representation of this, we can say that now the data is stationary. When we have taken the first order differentiation, the data is stationary. Now, as I was saying before, you need an experience, and also subjectivity is over there. A lot of subjectivity is there to a particular pattern. Somebody may be of the opinion that this data is stationary, somebody may say counterwise. Now, instead of going, although for explanatory purposes, this is fine. And even if suppose you are doing this forecasting using ARIMA, that is autoregressive integrated moving average method, then you use this. But normally nowadays researchers, they simply go to the test, and from the test they get a clear-cut answer whether this data is stationary or this data is not stationary. But nevertheless, you will find these diagrams of correlogram in textbooks in order to explain you the concept of stationarity. Now, so we move to the test for stationarity. Nowadays there are many tests, but we will stick to the most basic one, that is we go to the Dickey-Fuller test. Dickey-Fuller test, it is also called as Tau test. Now you take a pure random walk model. Is it a pure random walk model? It will be a pure random walk model only if theta is equal to 1. We take this model, and then what we do, we deduct yt minus 1 from here also, and yt minus 1 from this side also. From both the sides we deduct. So we get this yt minus 1 is equal to theta yt minus 1 minus yt minus 1 plus epsilon t. So now we can write it as yt is equal to theta minus 1 yt minus 1. Theta minus 1 you have taken in the bracket, common to yt minus 1 plus epsilon t. Now we assume that this theta minus 1 is my gamma. In Dickey-Fuller test, we do not need to test for normality. Although if you are doing t-test and all, we need normality, but it is not required over here in Dickey-Fuller test. Now we have assumed that gamma is equal to theta minus 1. So now we can write it as yt minus 1. We write it as delta yt. Delta yt is nothing but yt minus 1 is equal to gamma yt minus 1 plus epsilon t. So now see, if theta is equal to 1, if it is a random walk model, theta is equal to 1. So if theta is equal to 1, then 1 minus 1 gamma is equal to 0. And this is what we say, that this has this means there is a unit root, or meaning of unit root is the process is not stationary. If there is a unit root, this is also used in nomenclature. If presence of a unit root means the process is not stationary. So now, if, as we have seen in the AR processes, this value of theta 1 is less than 1. We have seen earlier that this is the necessary condition for the process of stationary. Then your gamma is less than 0. If theta is equal to 1, then if theta is less than 1, then gamma is less than 0. This means the process is stationary. So the null hypothesis, here the null hypothesis is gamma is equal to 0, the process is not stationary. Gamma is less than 0, the process is stationary. Now a few words about the star test. This star test doesn't follow the t distribution, and we do not take our t values from there. The table values for the star test were given by Dickey and Fuller themselves. So here the alternate hypothesis says that the process is stationary, and the null hypothesis says that the process is not stationary. Moreover, since the alternate hypothesis has a less than sign over there, this indicates this is a one-tailed test. It's not a two-tailed test. And in this case, since there is no mean parameter, so this is related to a process with a zero mean. So for a stationary process which is stationary around the mean, which is not 0. Now the next test, which you called as tau mu test. Tau mu means that is there is an element of drift. The previous test which we just now discussed was quite restrictive, as we have assumed that there is a zero mean over there. But here what we are doing, we are having a drift parameter. Having a drift parameter will ensure that the mean of the series is not equal to 0. We repeat the same process, minus yt minus 1 and minus yt minus 1. Meaning thereby both the left hand and the right hand side of the equations are deducted with yt minus 1. So yt minus 1 can be written as delta yt is equal to, now we take yt minus 1 common over here, mu plus theta minus 1 bracket closed yt minus 1 plus epsilon t. Again theta minus 1 is nothing but your gamma. So we can write it your final equation as delta yt is equal to mu plus gamma yt minus 1 plus epsilon t. Now herein again your null hypothesis, gamma is equal to 0, alternate hypothesis, gamma is less than 0. And another thing, the t values over here, the t values which are over here are not the same which were there in your Dickey-Fuller normal test without drift and without trend. There were no, the critical values over there and critical values over here are different. Now last we move to the case where there is a drift with drift and trend. This trend is missing over here, please note it down. So we are doing a Dickey-Fuller test, tau b, tau beta, you can say, and this is having a drift and also a trend. So if there is a trend in the data, the first test of tau and tau mu cannot be applied. So you have to modify your model in this format where you incorporate a trend element over there. So it is mu plus theta 1 yt minus 1 plus beta t minus or plus epsilon t. Now basically when there is a trend in there, so our emphasis is to identify whether the trend is deterministic or trend is stochastic. That is our main purpose over here. Like say suppose the series exhibits an upward trend. Now the purpose of unit root test is to test whether the series is consistent with I1 process, so that it has a stochastic trend, or it is consistent with I0 process, that is it has a deterministic trend. Now we do again the same thing. Again we both the right hand side, and please ignore this, we do minus yt minus 1 to both sides. That is, we do over here minus 1 and also here yt minus 1. Once we have done this to both the sides, what we get? We get delta yt is equal to mu plus, again we take this common. From this we take common theta minus 1 and theta minus 1, we assume it to be gamma. So we directly write it gamma yt minus 1 plus beta t. Beta t is your trend element plus epsilon t. Here the null hypothesis, gamma is equal to 0, alternate hypothesis, gamma is not equal to 0. So if your H naught is accepted, it has an stochastic trend, and if your H naught is rejected, means the alternate hypothesis is accepted, it means there is an deterministic trend. So we have seen all the all the three cases with just the simple one, and then with drift, and with and the last one was with drift and with trend. So basically your this Dickey-Fuller test is based on AR process. This is it's a stochastic process generated by ARP. They are referring to this equation where P means the number of lags that has been taken, like it is theta p yt minus 1. If it is only yt minus 1, that is 1 is taken, the p will be 1. If it is yt minus 1 and yt minus 2, 2 lags are taken, then p is equal to, and likewise. So the thing is, if we specify this as this equation, say is the original equation, maybe it is say extending up till 10, p 10 yt minus 10, and we have taken only this much of the equation. That is, we have taken only one lag term. So the impact of all the remaining lag terms, they will be sitting over there in Vt, in the error term. So we can say, what is Vt? Vt is nothing but all that has been excluded in this model. If we should have taken 3 lags and we have taken on, if we should have taken only 2 lags, we should have taken 2 lags, but we have taken only 1 lag. So the impact of theta 2 yt minus 2, it should sit in the error term Vt. So Vt considers all the lag terms other than that has been included in the model, that is theta 1 yt minus 1. And since these lag terms which are supposed to impact the dependent variable are present in the error term, then the error term will not be independent with its subsequent values. Expected value of ui uj will not be equal to 0. So there will be a problem of autocorrelation. So we have to estimate autocorrelation and check for it. Now the strategy to avoid autocorrelation is to increase the lag length. If you keep on increasing the lag length, all the necessary lags will be included. So also we should start with the maximum lag length, say P, as example, if you have say monthly data, then P should be greater than or equal to 12. Or nowadays, this is the proper thing is the proper thing is in all the softwares you have these criterias, lag length selection criteria, AIC, HQ, Hanan, Quenon, and SIC. All these are Akaike criteria. All these criterias are there. So based on these criterias, we will select the optimum lag that is to be considered. So since there is an option, there is a chance that there would be a problem of serial correlation, then we go for a different approach that is called as augmented Dickey-Fuller. This was given in 1976. Now in augmented Dickey-Fuller, what we do? We take yt is equal to mu plus theta 1 yt minus 1 plus theta 2 yt minus 2. Both the side we add and minus to the right hand side of the equation. Once we add and then we minus the same term. So in fact it will not have any real impact on the equation since we are adding and deleting it by the same term. So when we do that, when we add and minus, so then upon rearranging this equation, we can write it in this format. That is, we take in one case for yt1 these two terms as common. So yt1 minus yt minus 1, yt1 minus 1 is common. So theta 2 plus theta 1 in bracket yt minus 1. Then here theta 2 is common in this case. And we have over here yt minus 1 and yt minus 2. So we write yt minus 1, yt minus 2 and take theta 2 common plus epsilon t. So once we have done this, then what we can do, since this equation is, this is the final equation at the moment, now we deduct yt minus 1 from both sides, means here also minus yt minus 1, here also minus yt minus 1. So once we have done that, this can be termed as yt minus 1, it means epsilon delta yt. Now we incorporate this yt minus 1 also over here, so we get an additional minus 1, so it becomes mu plus bracket open theta 2 plus theta 1 minus 1 yt minus 1 minus theta 2. Now this is yt minus 1 and yt minus 2, this we can write it as delta yt minus 1 plus epsilon t. So we say gamma is this and theta 2 is and gamma and lambda 1 is this term. So now we can write it in terms of delta yt is equal to mu plus gamma yt minus 1 plus gamma 1 delta yt minus 1 plus epsilon t. Again the null and the alternate hypothesis, h naught gamma is equal to 0, h1 gamma is less than 0. So this, now in this process what we have done, we have added an additional yt minus 1, because of which the original equation is modified. Now once you have done this, so we can write this in terms of without intercept. This is the we can modify our Dickey-Fuller into this, and this is with intercept, and this one is without with intercept and trend. Now this the process which we have discussed, that is the significance testing using augmented Dickey-Fuller test, we will do it through the help of eViews. Let us take when we have the data in our software, we have inserted the series is X. When you go to the option of quick, you get unit root test, or you can click on this X and options will be coming up. See, there are so many tests which are available over here. Augmented Dickey-Fuller, Dickey-Fuller ERS, Phillips-Ferron, KPSS, and then Elliott and Nag-Perron. These tests, there are many tests over there. The process is almost the same, only for KPSS test, the null and alternate hypotheses are opposite. Phillips-Ferron is a non-parametric test, and there are some things like these in all of them. So at the moment we will just learn the basic process, that is we select the augmented Dickey-Fuller. Then when you are selecting augmented decouplers, see, at level means without doing any differentiation of the data, you have three options: intercept, trend and intercept, and none. This is what none means: when there is no trend, no intercept. This is intercept means when there is only a drift parameter, and the middle one is both, it has a trend and intercept. So these three tests, which the three equations which we have just before seen, all these three equations are incorporated over here. Now you can lag length also there. So at level you have to check for the first equation. First equation is this none as such, which we have discussed. This was the first which we have discussed. This intercept was the second one, and this trend and intercept was the third one. So once you have checked it through this, then next time you will select the second option, first difference. And again you will do for all these three separately. That is the process over here. So then that is what I am showing. We can again, using first difference, we can do for intercept, then we can do for trend, then we can do for none. See here we have selected. Now you are asking the software that don't do this unit root test on the raw data, but rather do it on the first difference. Again here you will find all these criteria which we have discussed earlier also. Akaike, Schwarz, Hanan, Quenon. You can take anyone. There is at the moment we don't go into the depth of this, but for you can take any one of this: Akaike, Schwarz, HQ, or any one of this. That is fine. Now once you have done this, full table will be coming up. As it is a very big table, we will not be able to understand it very clearly over here. But only thing is, we need this value in order to understand. We will come just in the next slide, it will be clear. Now see, we have done just for unit root, and this is we have done on the raw data, and this is the first case. Now in the first case, what we see, this is the T statistics which is to be tested. Here we don't have to look at any other thing. We can simply look at this value, and the criteria, we normally do testing at 0.5%. So 5% means 5 by 100, that is equal to 0.05. 0.05 is the cutout. If the value is more than this, it is not significant. If the value is less than this, it is significant. If the value is more than this, not significant, it means the data is not stationary. And if it is less than this, it means the data is stationary. So when we take the first equation, this is 0.07, it is more than this, the data is not stationary. Next time we take the second equation, constant, and we have taken the linear trend also along with it. We have again taken a linear trend. Again this value 0.05, this value 0.1275 is more than this, so it is not stationary. Again we repeat the process. It is none. It means there is no drift parameter and no no trend. In this case again, this value, the probability value is more than 0.05. The moment it is more than 0.05, it is not stationary. So we have tested for constant with a drift, with drift and trend, with no drift and no trend. In all these three, our p values were more than 0.05, and hence we can say, and that the statistics is also given over here, but we normally don't need these things. We can simply interpret with the help of probabilities. And softwares have made our life much easier. Now what we do, see, in this up till here it was just your simple X, means you had taken just the raw data. Now you ask the software to do it at first difference. So that's why you see it is written now, we are not we're testing the stationarity of x, rather we are testing the stationarity of dx, means first order differentiation. Now the moment we do 0.05, it is no longer more, it is less than 0.05. So it means the process is now stationary. You can also check it for when you have, in this case, in the earlier case, it was in the constant one, means there was a drift parameter. In the next case, there is a drift parameter plus there is a trend element. For this also again, this is 0.0001, that is less than 0.05. It means it is stationary. In the third case, again we are doing with dx and none. It means no drift, no trend. Here again it is 0.0000. It means, or it indicates that there is no problem of, the data is stationary. So I hope that you have understood the concept of autocorrelation function, how you can identify whether a process is stationary or not using the using the correlograms, and then you have understood the process of Dickey-Fuller and augmented Dickey-Fuller test, and also now using a software, how you can identify whether your series is stationary or not. Thank you.